All right, so yesterday we were talking about horizontally projected projectiles and projectile motion in general, okay? And we said that for any object that is projected horizontally, so a car that drives off of a cliff or a person that runs off a diving platform or any of those kind of things, okay, that we have to remember a few things about that motion, okay? One of the most important things we have to remember for a horizontally projected object is that its initial vertical velocity is what? Is zero. Okay? If it is projected horizontally, it is not moving vertically at time zero. Okay? That is probably the most important thing we need to remember for horizontally projected projectiles. Okay? Now, in the question we have here, okay, that's one of our givens, we're looking for how high the cliff would be. Is that a vertical or horizontal variable? It's a vertical variable, okay? And we would call it the vertical displacement. The height of the cliff is the vertical displacement, okay? And then we have that they are running off of this cliff at 8 meters per second. Is that vertical or horizontal? That's horizontal. Okay, horizontally, does their velocity change? No. Okay. Horizontally, whatever velocity you have, that's the velocity you have horizontally the entire time. We're working in the perfect physical world where there's no air resistance or anything that would slow you down. Okay, and they hit the water 15 meters from the base of the cliff. Horizontal or vertical? That one's horizontal. Okay, it's measuring. They traveled this far, 15 meters from the base of the cliff, right? Because they would do this. That's how far they traveled horizontally. Okay? So, 15 meters. Okay, so we are looking for the height of the cliff. Do we have any other vertical information we can write in there right now? What else do we know vertically, guys?
Acceleration due to gravity.
Right, acceleration due to gravity. Okay, so if I want to find the height of the cliff, I need at least one more piece of information vertically. What could I get right now?
Time.
I can get time. I can use the horizontal data to get the time. Time is the only thing that goes on both sides, both the vertical and the horizontal, and I have enough information here provided I recognize that the object travels at a constant velocity horizontally. Right, so then I can solve for time. T will equal d over v. Okay, so that'll be 15 meters divided by 8 seconds. So that's going to be 1.875. Is that right? Okay. Okay, so 1.875 seconds is what that's going to come out to. Now can I find, oh, look at that. It's on there from yesterday. Mind like a steel trap. Okay, so I got to solve for d. Do I have a formula that will do that? Okay, is it the same one we used on every single question so far? No. Okay, so this is 0. All right, all I have to do is plug in my numbers. Okay, so 1/2 times 9.81 times 1.875 squared. I'll bet that calculation is still in the calculator. It is. Okay, so that cliff is 17 meters high. Actually, we only have one significant digit here because of this. So my answer isn't going to be 17. It's going to be this, and it's going to be weird. (17) to one significant digit is 20, or 2 times 10 to the 1. Okay. I will never give you a question whose significant digits will end up as 1 on a test or a quiz. Okay, just it's weird. Okay. All right, making sense? All right. Are there very many things I can ask you to calculate in a horizontal projection question? I can ask you to find the height of the cliff. I can ask you to find how far from the base of the cliff they hit. or I can ask you how fast they went off the cliff. That's really it. Okay? And we've done now, like, I think 2 of each one. Okay, so we've got lots of examples there of the horizontal ones. Okay? Now, the other type of projectile motion is projectiles that are projected at an angle. Okay, so if I launch something like this, okay, what's its path through the air going to look like? Right? It's gonna arc through the air, right? It's basically gonna do this. Okay? It's gonna make a projectile arc that will come back to the ground, right? If you're ever, like I think I used this example before, playing with a hose, right? If you're shooting the water will make that arc. Okay? Anything makes an arc like that. Throw anything, and it'll make that arc. Okay? Can you ever throw something and have it go straight horizontally? Absolutely not. It's always going to drop a little bit. Now, the faster it goes, the less you'll notice that. But okay, we even watched that Mythbusters thing with the pistol, right? That thing still dropped. It was moving really fast. That bullet still dropped, okay, over that even short distance. So it's always going to have this arc. Now, what if I wanted it, instead of hitting here, to hit over here? What could I do to make it go over there? Okay, so I could aim it higher, or
You can put more force in the throw.
right, I could launch it faster. Okay, either one of those things could make it travel further. Okay, if it goes faster, it'll go further. If I aim it higher, it'll go further. Right, to a point. Is there a point where that stops working? What angle will it start coming the other way? 46 degrees, right? Once you get to 45, that's as far as it'll go. You start going back this way, it's gonna start coming back, right? Okay, once you get past the halfway mark, it's gonna start coming back to you. All right, so if I launch something at an angle, is it still moving both vertically and horizontally at the same time? What do you think? I think so, okay? It's gonna travel, okay, from this point to this point horizontally at still a constant velocity. Vertically, what's it going to do? It's going to go up and then come back down. Okay? If I was watching this from like head on, so I really couldn't see the horizontal part of what it was doing, I would see an object that's launched, I would see it do this. I would see it go up and come back down. Okay? If I couldn't see the horizontal part of it, that's all I would see is an object that goes up and then comes back down. So, if I launch something like this, and I know, let's say that the launching speed is 100 meters per second, and the launch angle is 30 degrees, could I calculate how fast it's moving horizontally and how fast it's moving vertically with that? Is it just finding vector components? Okay, that's why we do this last. You have to know how to find x and y to do projectile motion. Okay, if I found this side here, that would be the constant horizontal velocity that the object would travel at. It's the horizontal component of the launch velocity. Okay, what would this side be? Is that a vertical line? Okay, so it's something about the vertical stuff, right? Vertically, does it change velocity? Yeah, because gravity's going to grab it, right? Gravity's going to pull it back to Earth. So this isn't a constant velocity, it's the initial vertical velocity. Because once it's launched, its vertical velocity is going to change. Okay? Once I throw something into the air, gravity is already pulling it back to Earth. Its vertical velocity is changing the instant it leaves whatever launched it, my hand or a cannon or whatever. Okay? Everybody with me there? Making some sense? Okay, so if I can find those two things, and I would probably know some additional stuff, like vertically, okay, I'd be able to calculate VI. I'd already know this number. Okay, can I start calculating things? I can, but I have to understand one or two other things. If I throw this marker up in the air, okay, so let's say it's going to leave my hand at this height. I'm going to catch it at the same height. Okay, when it comes back to my hand, how fast is it going compared to when I threw it? I'll do it in slow motion. So it's going to leave my hand, okay, it's going up, 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 but it's slowing down, slowing down, slowing down. When it gets to here, how fast is it going? 0. At its highest point, it stops for an instant and then begins to fall back down. Okay? It falls exactly the same distance at exactly the same rate of acceleration. So if everything is the same up and down, when it comes back to my hand, it should be going the same speed that it left my hand at. Perfect physical world, of course, okay? Because in the real world, things would tumble and slow down, but we're dealing with the perfect physical world. So if I throw something up in the air, or I throw it at an angle, when it comes back to Earth to the same height, okay, it's going the same vertical velocity in the opposite direction. Instead of up, it's down, okay? This is why if you were to, let's say, shoot a gun into the air, you shouldn't wait around. Okay? I mean, if you shoot a gun straight up in the air, you should not stay there. Right? I mean, in the perfect physical world, not in the real world, okay? But in the perfect physical world, if I shot a gun straight up in the air, the bullet would come right back down and go right back inside the gun. At exactly the same speed I shot it at. That would be bad. Okay? That would hurt a lot, I would think. Okay? Because it would go back into the gun and probably force my hand down and things like that. Okay? So in the perfect physical world, that's what would happen. In the real world, do I have to really worry about that too much? No. Because in the real world, the bullet will go up, but it'll slow down. And then when it falls back to Earth, it'll tumble. Okay? Which means it won't go as fast. I still wouldn't wait around for it if it were me, but okay, it will tumble and it won't be going as fast in the real world. Okay, so if I know, can I calculate VI right now with these numbers? Okay, so let's do that. Okay, what side is VI of this triangle? Opposite. Okay, so to get VI, I'm going to go sine of 30 times 100, which should be 50. Okay, 50 meters per second up. Now, acceleration due to gravity does have to be negative because this object's going to change direction. It starts upwards and then it ends downwards. So if we're talking about the whole flight, when it comes back to here, VF will be 50, negative 50. Okay, so that's something we have to remember. Right? In a projected at an angle question, VI and VF vertical are going to be the same number, provided it comes back down to the same height. Okay? Now, what would my displacement vertically be in this situation? 0. Goes back up, comes back down. Okay? So it'd be another number I could have if I really wanted it. My vertical displacement would be 0. Okay? But right now, with that information, could I calculate how long this thing is in the air? Right, I got VF, I got VI, I've got A. Right, I could calculate that. So knowing that you could now calculate time, here's what I want you to do. How far horizontally is this object going to fly? Okay? How far from the launch point is it going to fly before it comes back to the ground? Okay, so you already know you can calculate t with this information. What I'm looking for okay, is the horizontal displacement. Okay, give you a minute on that. If I want to find the horizontal displacement, what do I need? I need time. Okay, so I'm going to use the vertical information to get that. I'm simply going to go T equals VF minus VI over A. So that's going to be negative 50 minus 50 divided by negative 9.81. That way I don't get a negative time. Just because I'm flying through the air doesn't mean I'm going back in time. Okay, so we're going to have, okay, negative 50 minus 50, which is going to be 100, obviously. Okay, negative 100 divided by negative 9.81. Okay, so this thing is going to be in the air for 10.2 seconds, roughly. I'm going to bring that over here because time is the only thing that can be used for both sides. And now I can solve for D. D will equal V times T. Oh, sorry, I can't solve for D yet because I don't have V horizontal. How do I get it?
100 cos 30.
Right, 100 cos 30. It's the adjacent side in this triangle. It's the horizontal component of the launch velocity. Okay, so cos of 30 times 100, it's like 86 point something, right?
Yeah.
Times 100. Okay, so 86.6 meters per second. Okay. And then we'll just do that calculation there, the 86.6 times the 10.2 seconds with all the decimals. Okay, this thing's going to travel 8.8 times 10 to the 2 meters. Okay, everybody all right with that? Okay. One other thing that projectile motion problems sometimes ask for. Occasionally, they'll ask for the maximum height achieved by the projectile. Okay? So if I'm looking at this arc, when does the object hit its maximum height? Think about when I threw the marker up in the air. Okay? In terms of time, when does it hit its maximum height?
The moment before it starts dropping.
Right, the moment before it starts dropping, which would be the halfway point, right? Half the time it's going up, half the time it's going down, so right smack in the middle, okay, would be where that maximum height is. So height is vertical displacement. VI is still the same number, okay? We're still dealing with the launch here. What's VF when the object is at its maximum height? 0. Remember when I threw that marker up in the air, I said it stops for an instant at its maximum height because it's slowing down, slowing down, slowing down. Okay? So if I want to calculate the maximum height or maximum vertical displacement, okay, I need to understand that when it's there, its vertical velocity is 0. Or that it occurs at how much of the time? Half. Okay? There's more than one way to do this. You can solve for D when the time is half of its full value, which was 10.2 seconds, so at 5.1 seconds, right? Or I can simply say that VF was 0 at that time and solve for D. Okay? That's the way I prefer to do it because I find people forget to divide the time by 2. Okay, when they do that, and then they get the displacement, the maximum height is 0. Why do they get the maximum height to be 0 if they forget to divide the 10.2 by 2? Because they're dealing with the whole flight. And when it comes back down to here after 10.2 seconds, it's back on the ground and its displacement is 0. Okay? So here's what I do. I keep this number because it still applies. I keep this number because it still applies. Right? And I change this number. VF is no longer negative 50. VF is now 0. So I have VF, VI, A, and I'm looking for D. Alex. Hi. Yeah. We're working on something here. I just don't want you to miss anything. Okay, so now VF is 0. Do I have a formula that'll calculate D if I have VI, VF, and A? Which one? Yeah, the VF squared one. Okay, I've got that formula there, and I know all the parts of that except for D. Right, so all I'm going to do is manipulate that for D, and that'll tell me the maximum height. Right, so I'm going to go VF squared minus VI squared divided by 2A equals D. So when I plug in my numbers, we said at the maximum height, the final velocity is 0, minus 50 squared, because that was our initial velocity. Okay? And then we would divide that by 2 times negative 9.81. Okay? Okay, so that object is going to reach a maximum height of 1.3 times 10 to the 2 meters. 130 meters off the ground. Travels 880 meters horizontally and reaches a maximum height of 130 meters. Okay. These are some of the things you might get asked for in a projected at an angle projectile question. Okay? All right, now I'm going to show you a video here that was like viral when YouTube was brand new. So that's a long time ago, okay, right before you were born. Okay. And people debated for a very long time whether it was real or not. Okay, so I'm going to show it to you, and then you can think about it for yourself. So if we're looking at this situation here, okay, as with any projectile motion question, we still want to break up what we know into the 2 dimensions of the motion. Okay, that's vertical and horizontal. Okay, we know vertically speaking that the acceleration is gravity, so negative 9.81 meters per second squared. Okay, VI is the opposite side of that projected triangle, so that's going to be the sine of 30 times 20, which will be positive 10 meters per second. Since the launch point and the pool are level, VF is negative 10. Okay, horizontally speaking, right now, all I can calculate is the horizontal speed, okay, being the adjacent side here. So the cos of 30 times 20. Like 17 or something like that, right? Cos of 30, 20, 17.32. Okay, meters per second. All right, I'm trying to find how far away to put the pool. That would be the horizontal distance traveled by the guy flying through the air. Okay. What else do I need? Time. Are we always finding time in these questions? Yeah. Okay. So I've got A, VI, and VF, vertically speaking, and I've only got one piece of information horizontally. So I would say this would be a good way to get the time using the vertical information. Right, so that's going to be negative 10, okay, minus 10 divided by negative 9.81. So negative 20 divided by negative 9.81. All right, so they're going to be in the air for 2.04 seconds. All right, time is the one thing that can go to both dimensions. Okay, so 2.04 seconds. D equals V times T. So I take that 17, okay, so, and I multiply it by the time times the 2.03. All right, 2 significant digits there. 35 meters away is where you should put the pool. And then pray. All right. Okay, remember, quiz tomorrow. Acceleration and graphing. It's the one we postponed from last Friday. All right. Same ones. Yeah. Okay.